acting Chem 20-like, and complete an ICE table, okay, which is I stands for what you have at the beginning or initial, C is the change, you know, plus something or minus something, E stands for how much you have at the end. So in this example, the recipe says you need 4 units of HCl for every 1 unit of oxygen, and you get 2 units of water and 2 units of chlorine gas. And we happen to be starting with 5 units of HCl, hydrogen chloride gas, and just 1 unit of oxygen gas. So the first thing you'd have to do last year is figure out what's going to run out first, what's going to limit the reaction. So we're looking at, for every 4 of those, we need 1 of those. There's no number, so blanks we treat as a 1. Okay. And in this particular case, we've got 1 unit of oxygen that matches the stoichiometry, and we've got 5 units. We've got more HCl than the recipe calls for. There's an extra unit. Okay. Oxygen is our limiting reagent in this case. That's what would go to 0. All of that 1 unit would run out because there's extra HCl. There's 1 extra unit. Okay. So we would have said all of that would react away. Okay. To predict this stoichiometry, okay, hopefully required over given, rings some bells is a little familiar. Okay. Multiply to take 1 C and convert it to another C. That's where we really do stoichiometry. We use these ratios, multiply by the required coefficient. I want this C, and that change is a 4, divided by the required, by the given coefficient, which is a 1. Okay? That's the showing we need 4 times more. Okay? So 4 units of HCl would react for every 1 unit of oxygen, okay? Which would leave 1 of these left over. Okay? On the product side, we wouldn't start with any products. If we look at how much water would make, we could pick either stoichiometric coefficient to figure this out. If we take this 1, I'll do required over given, okay, and we only do stoichiometry with the C values. Okay, we can't do them with the E's, we don't do them with the I's, just the C's. To figure out how much water, the required coefficient is 2 for water. The given coefficient, I'm going to use this number, and its coefficient is 1. So multiply by 2, divide by 1. And that's kind of what our recipe shows us. We get double the amount of water compared to the oxygen that gets used up. Okay, so we're going to see 2 units. Okay, now I put -4 and -1. These are products, so they're going to be plus. They're going to be made. Now Cl is exactly the same coefficient as water, so they're made in the same amounts. So we'd get 2 units or moles of water and 2 units of chlorine gas. Last year, I would have always done these ICE tables in moles. Okay. So that's Chem 20. If you don't like this, you don't remember it, or he did that really fast, we're not going to be doing this year. We're not going to have any limiting reagents this year. No LRs and excess reagents, because we're going to look at equilibrium that can go both ways, that don't totally go to completion. Okay? So this is a lead into what about the reverse reaction? Okay. Could water bump into chlorine gas and make some hydrogen chloride gas and oxygen gas? Okay. In this unit, we're just going to study those reactions that yes, the reverse is possible. Not only can the reaction go forwards, but it can then go backwards. And we're going to find out where it ends at. What amount of chemicals do we have at the very end? Now I've color coded the next piece red. I wanted in the notes, I don't want you to write it down. It's a lot of words and it's kind of a waste of time, but I want to mention many chemical reactions can go in both the forward and reverse. Okay? But I put many, not all. You will never burn a piece of wood and then come back later and the CO2 and water went backwards and the wood showed up again. Okay? That will never happen. Not all reactions do this, but some do, and we're just studying the ones who do. Okay? The equilibrium reactions will come to some balance between fully turning into products and fully being reactants. Okay? When this goes to 0, we've made it all the products we could. Last year in Chem 20, you only learned 100% reactions. This year we'll learn ones that maybe go 50% forwards, or 10%, or 1% forward. That's the world we're going to be diving into. Okay. So equilibrium is going to require some conditions. The first thing we're going to need is a closed system for a reaction to go both ways. Okay. So if you had a reaction with magnesium metal and some hydrochloric acid and you made magnesium chloride and hydrogen gas, okay, if you don't have a closed system, you're going to lose that gas. And if you lose that gas, the reaction can't go backwards because it's missing the product for the reverse reaction. Okay. So many equilibrium require a closed system. Okay. They all require a circumstance that you're not losing the products. Second, a property of equilibrium is that we're going to have what's referred to as dynamic equilibrium. And this is going to be addressed more throughout the early part of this chapter. That's when the forward reaction equals the reverse. And the big thing I want to introduce is new arrow notation. I left the arrow blank. Okay. In equilibrium reactions, we have a forward reaction, which I'm doing a single hook arrow, and there's a reverse reaction. So I'm going to show an arrow going backwards. Okay, and these are the type of arrows we're going to be using in equilibrium. Okay. A system has gone to equilibrium when the rate of the forward reaction equals the rate of the reverse. So maybe the forward reaction is making 2 moles per liter per minute of water, and the reverse is using up 2 moles per liter per minute of water, exactly canceling each other out. Okay, so the concentration of water stays the same. That is dynamic equilibrium. Okay. I'll just put that in notes. So maybe the system is making 2 moles per liter per minute of water, and it's also using 2 moles per liter per minute. Okay. I obviously made up the number. The key is that the number is the same. The amount being made and the amount being used match each other. Okay. A few definitions, and then I'm going to roll into a case study and then talk about arrows a little bit more, and then we'll be largely into math and calculations for most of the rest of this lesson. Okay. Okay. So color-coded these. The black are most important for Chem 30. So the first definition would be phase equilibria. Okay. So this is an equilibria between 2 phases. One you're very familiar with, maybe not written as a chemical reaction, but water in the liquid phase to water in the gaseous phase, water vapor. That'll be an example of a phase equilibrium. Okay. Okay. NaCl solid in equilibrium with NaCl aqueous. Okay. Chem 30 is going to focus on the black, chemical reaction equilibrium, okay, where we've got reactants and products, reactants going to products and their chemical changes. I mean, the phase equilibrium is a physical change, not a chemical change. Okay. Dynamic equilibrium I started to introduce on the previous slide. Okay. This is definitely a tested concept for quizzes, tests, diplomas. Okay? Okay. When you're at dynamic equilibrium, the concentration of the products and the reactants are constant, okay? Because they're being made and destroyed at the same rate. And we're going to be doing some percentage yield calculations. So I'm going to turn those words in percentage yield into an equation that we're going to be using. It's the ratio of the amount of product measured at equilibrium. So I'm going to refer to this to the actual amount of product. Now, you can use any units you want. If it was a gas, you could measure how many liters of product or how many moles or what the concentration is or the mass. It doesn't matter as long as the units you use on the top, the numerator, are the same units in the denominator. On the bottom, we're going to put a theoretical amount of product. If the reaction happened 100%, like you learned in Chem 20 Stoic, how much would you have gotten? So the theoretical max. We're going to do some calculations on the next slide. So this is a hypothetical. It's if the reaction was 100%. We're going to look at 3 case studies on the next slide and do the percentage yield for each of those 3 case studies and see how the percentage yield varies. Is everyone okay? So I have 2 more rows hidden underneath this table because there's going to be 3 case studies. You can just see the first one. Okay. I didn't have the arrow put in, but I'm handwriting in an equilibrium arrow. A hydrogen iodine reaction. Hydrogen gas, diatomic hydrogen plus diatomic iodine makes 2 hydrogen iodide gas. In our first case study, we started with 5 moles per liter of each reactant and no product, kind of what you're used to. You dump in reactants and we'll see how much product's made. At the end, hydrogen gas went down to 1.1, iodine gas went down to 1.1, and hydrogen iodide made 7.8 units. So in our first case study, the numerator is how much product you actually got. If you have more than 1 product, you have to pick one for this calculation. It doesn't matter which one. We only have 1 product, so I have to pick hydrogen iodide. So there were 7.8 units made, and I have to do a Chem 20 type Stoic calculation for what is the most that could have been made. Okay. So we've got to look at our reactants and say, what if one of these totally ran out and went to 0? Okay. Now these are in perfect balance. One of these needs one of those, so they react in equal amounts and they're starting in equal amounts. So they're a tie for the limiting reagent. So I'll just keep using hydrogen. Okay. If we started with 5 units of hydrogen and it all went away, what does the recipe tell us for how much product we would make? Okay, our recipe is saying this reactant, if it totally reacts, should make double the amount of product. So this 5 would double to 10, would be the most that could have been made. Okay. I'm just not using units. This could have been moles per, as long as it's the same units on the top and bottom, it's fine. So 7.8 divided by 10 times 100 is 78%. So this reaction went 78% forward. Didn't go 100%, didn't go the most it could have, went most of the way there, well past half. Okay. If it had only gone halfway, we would have had 5 units of product and half of the reactant left over. Okay. But it went 78%. Okay. Second case study, and this is going to get a little weird. You've never really seen this before. There was product dumped in at the start. That would have made no sense last year. So we have half a unit of hydrogen gas, half a unit of iodine gas. So they're in equal proportions. They're a tie for the limiting reagent. And we dumped in 1.7 at the beginning of product. And we see the reactants, hydrogen went down a little bit, iodine went down a little bit, and the product went up even higher. We're going to do the percentage yield again and see how it changes under this second circumstance. So how much product did we actually get? That's the easier. There's only one product, 2.1. Now this is the hardest one to predict, the max product. Okay. The max would be if we keep this 1.7, that's a product. It's dumped in at the end, but we still call it, it's still a product. So the max would be if we keep that 1.7 plus we make as much as we can more. Okay. We're starting with half a unit of hydrogen gas. We've got the same stoichiometry. Our recipe says double the amount of product. So this half could have doubled into one more unit of product if it all reacted. Hopefully that makes sense to everyone. Start with 1.7, and then this half could have doubled into 1. What does that turn out to be to tenths? Anybody? Turns out to be about 78% again. We got the exact same number. So if we start with all reactants, we get 78%. If we start with sort of this humble jumble, let's throw a bit of everything in, including products, we got 78%. And our last case study should be the weirdest yet. We're going to put in no hydrogen. We're going to put in no iodine, no reactants whatsoever. Last year, you'd say, well, nothing happens. If I have no wood and no oxygen, nothing should burn. Okay. We're going to dump in 3.2 units of products. And something really weird happens. We started with no reactant, and we made a bunch of reactant. This reaction went backwards to get to dynamic equilibrium. Okay. We made some iodine, and our product went down. It's never happened before. Okay. Products aren't supposed to go down. Well, they can in equilibrium situations. Okay. And when we do this calculation, how much product did we actually get? Well, that's how much product we actually had. Okay. What's the most we could have had? Any thoughts on that one? Pardon? Yeah, the most you could have is if that 3.2 just stayed. Times 100, and lo and behold, you get that same percentage yield. No matter what you dump in, this reaction gives you 78% yield. Okay? Now, I didn't put this in at the top. The temperature has to be a controlled variable. Okay? If you mess with the temperature, the percentage shifts. Okay? But at a given temperature, you always get the same percentage yield for a given reaction. Okay? So for hydrogen gas plus iodine gas, it just goes to 78%. Okay? So we're going to talk about some arrows, and then we're going to move into calculations. We start talking about percents. We'll use them a little bit, but for most of the calculations, we're going to use equilibrium constants instead of percentages to define a reaction. You're going to have all kinds of tables in your booklet with equilibrium constants. So the concept is the same, but we're just going to use a different form to express this. Okay. So our arrow notation. Okay. We've got a couple options for equilibrium arrows. Okay. I got 4 boxes. I'm just putting arrows, so 1 or 2 lines is tons of space. This doesn't have to be a huge table. So we got what is the percent yield, what's the position of the equilibrium, what's the symbol or symbols. If you have a 0% yield, you have made nothing. Nothing's really happened. You dumped in reactants and 0% was the progress. So this would be all reactants. Okay. Really, it's no reaction. This is boring. There's not much to study here. The notation you might see for this to say there's no reaction is an arrow with an X through it. We're not really going to use that. Okay? In a later unit, we're going to, in redox, some reactions don't occur, and we call them non-spontaneous. This would be a reaction that's non-spontaneous, that doesn't occur. Okay? So not going to study much there. Okay? We're going to live, this is going to be half of our world for the next week or two. Less than 50%. Okay? So the reaction went 5, 10, 15, maybe 20%. Just a little bit. We call this reactants favored. There's a large percentage of reactants left over. There is a small percentage of products. To try to express this, the most common way we're going to do it is an equilibrium arrow, but then note that percentage up above. So I'm going to put less than 50%. Okay. A less common way, I'm not going to use this one very often, but it is acceptable, is to do a little arrow forward and a bigger arrow in reverse to show the reaction is biased towards, it goes backwards more because it's a small percentage. We're going to move to over 50%, and now it's going to be the reverse of this row. Greater than 50%, we made lots of products, product favored. And now I'm just going to flip the arrow format. Now it's equilibrium arrow greater than 50%, or a larger arrow in the forward direction, a smaller arrow in the reverse. In terms of what course do we study these? Well, no reaction is kind of not really a heart of any course. These two are the heart of Chem 30 AP and then Chem 35 AP, equilibrium. The last, often it's called 100, but I want to convey to you 99.9 we treat as 100. Okay? So 99.9 or 100, okay? This is all product. And that's where you use the arrow that you're used to, the one-way forward direction, and this is Chem 20. So you've left that world. You're learning new stuff about that world. You have that knowledge from Stoic.